All right, hello everyone. Today I'm going to be going over some stuff that you'll probably end up seeing in organic chemistry too. This channel has mostly been for Organic Chemistry 1 with Dr. Daddy, but I wanted to go over some of the stuff that you're going to see in Orgo 2 in this video and hopefully future videos if I can, and help you guys along with that. Even though I'm not really a teaching assistant for that class, I still want to be able to help you as much as I can. And so today we are going to be going over something that has to do overall with dienes, which also sort of feeds into allylic sort of compounds. And I'll go over both of these in a second. But first, let's talk about roughly what a diene is. So just to recall from Orgo 1, diene comes from ene, which means alkene, so something with a double bond, a carbon-carbon double bond, and di means that there are two of them. So diene means that there are two double bonds within in a carbon structure. All right, and there are a couple types of dienes. There is the cumulative diene, which essentially means that we have two double bonds on two separate molecules. So they're a cumulative diene because together we have two alkenes, two double bonds. So we sort of consider this a diene. But what we're more interested in are the dienes that are on the same exact compound. One example of this will be the isolated diene, which essentially means that we have a double bond, one or more than one bond away from the other double bond. So what that means is, okay, so I have a double bond right here. The next double bond is 1, 2 bonds away. So this is an isolated diene. And you'll see why we sort of call it isolated in a second, because we are now going to be talking about a conjugated diene. Essentially, this means it's a diene with only one single bond between the two of them. And we call this a conjugated diene because it has a resonance structure. And you may not be able to see it right now, but if I move the electrons from one of the double bonds onto that middle single bond there, this double bond has to break and electrons have to go onto the other carbon there. And I'm going to quickly draw my resonance structure arrow here. And we can see that our final resonance structure ends up with a positive charge over here and a negative charge and an extra electron over here. Now, the reason why these conjugated dienes are so important to us is because they are so stable and they also create a very stable addition product. So I'm going to clear my screen. Let's say we have a conjugated diene like this, and one of those double bonds go away and we end up with this here. So of course we did an addition reaction. We added something to this carbon right here and left a positive charge on that carbon there. And as we saw before, we can see, oh, we can make a resonance structure here. And so then we draw the resonance structure here and we have this. The positive charge moves right here. The double bond moves right here. Now what we have here is something called an allylic carbocation. And of course, it's an allylic carbocation because we have a carbocation. But we can also have allylic radicals, which will generally have the look of this. Allylic carbanions, which will look like this. And then finally, our allylic carbocations. We are probably more likely going to see these allylic cations over the allylic radical or the allylic anion. But you will see the allylic radical, or you should recognize it from before, from the radical reactions that we did before. And the reason why you should sort of at least have an idea of what it is because all three of these allylic compounds are extremely stable. So if we recall, let's take carbocations as an example. If you recall from nucleophile attacks, nucleophile addition, we remember that a tertiary carbocation, essentially a carbon with 3 bonds that has the positive charge on it, is more stable, so I'm going to put a greater sign here, than a secondary carbocation with 2 carbon-carbon connections, which is more stable than a primary carbocation, which only has the 1 carbon-carbon connection. And so then we can see over here, the most stable form of a carbocation for our purposes is going to be this allylic carbocation. And that's why it's so important to know this. And we can therefore understand why dienes are so important, because these carbocations come from conjugated dienes when we do an addition reaction. So that's where all of this ties in together. And now we are going to sort of talk about the addition reactions sort of associated with these conjugated dienes. So I'm going to clear this. Let's say we have a conjugated diene right here, and we want to, actually let me make it look like this actually, just to make it a little bit more intense, I guess, for our purposes. So let's say that we're doing a hydrohalogenation. Let's say we're adding HCl. And if you recall from Orgo 1, whenever we do a hydrohalogenation with any type of alkene, whether it be a diene or just a regular alkene, the hydrogen is going to end up being added first, and we end up with a carbocation. Okay, so this is where things get a little bit tricky, because there are several places that we can add the hydrogen to. We can add one here, we can add one here, we can add one here, or we can add one here. So essentially, wherever there is a carbon attached to a double bond, we can add that hydrogen to and cause the other carbon to become the carbocation or have that positive charge. So let's take these one by one. Let's start with this pink one. I'll call it A. If we add the hydrogen to that guy, this double bond right here will stay the same. Everything's the same over there. But now we have the hydrogen added right here, and thus this carbon here will have that positive charge. Okay? So now let's look at carbon B, which will be the orange carbon. Again, everything with that other double bond will stay the same, nothing changes, but now we're adding the hydrogen right here, and now the positive charge is over there on that other carbon, okay? So now let's look at carbon C, the green carbon. Now, unlike the other two before, this double bond right here will be the one that remains unchanged. So if we add the hydrogen right here, the positive charge ends up right there. And finally, if we add the hydrogen to carbon D, again, the other double bond will remain the same. The hydrogen is added here, and then we have our positive charge right here. So now what we're going to do is we're going to look at each one of these possible carbocation intermediates, and we're going to determine, which one is the most stable. So essentially what we're going to be looking for is our allylic carbocation. So obviously B is not allylic. That positive, sorry about that. The positive charge is too far away from that double bond. Remember, the positive charge has to be on the carbon next to the double bond. So that makes this not allylic. Same thing with when adding to the C carbon, too far to be allylic. Now we look at A and we look at D. Both of these are allylic carbocations, but now we have to decide which one is more stable. And the way we do that is we use the same rules as before. So we know that they're both allylic, so they're both pretty stable. So next we say, okay, where is that positive charge? What type of carbon is that positive charge on? For the carbon A, where we add the hydrogen to, this is a secondary allylic carbocation. For carbon D, where we add the hydrogen to, we have a tertiary allylic carbocation. As a result, we're going to call this carbocation intermediate D the more stable, and thus the intermediate we are going to form with this whole hydrohalogenation. All right, so I'm going to erase some of this stuff really quickly. And so then what we're going to do is we're going to say, okay, great. So now we have our intermediate, our carbocation intermediate. What do we do with that? So essentially, we're going to do whatever we did before with hydrohalogenation, aka add the halogen, okay? But what's important to note here is, again, remember, allylic carbocations will have a resonance structure. So let's go ahead and draw that resonance structure here. The double bond will move here, and we end up with the positive charge moving right here, right there. Okay? So now we have these two resonance structures. And if you remember from this, again, you don't have to remember this. I'm just saying draw comparisons back to the radical chapter, the radical reactions. Whenever we have this allylic carbocation or an allyl, just in general, we can end up with two possible products. One, where the positive charge stays the same, it stays on that tertiary carbon, and another for the resonance structure, where the positive charge moves right here. So let's call this product 1, and we'll call this one product 2. So product 1 will have the carbon added to, or the chlorine rather, added to this carbon right here. So here is our chlorine. So our hydrogen is added here, our chlorine is added there, and our double bond stays exactly the same. For product number 2, we can see that, the double bond has changed places because we're using this resonance structure now. Oops, sorry, I meant to erase that. And so that means that our hydrogen is over here, and now our chlorine is over here, okay? And so now we have these two different products. And these two different products have names that depend on where you've added your hydrogen and where you've added your halogen, okay? And so the way I'm gonna do that is I'm going to start numbering at the hydrogen, or at the carbon with the hydrogen was added onto. So this is gonna be carbon 1. Okay, same over here. And so now I'm just gonna start numbering to the left towards the other double bond to see what number carbon our chlorine was added to. Bear with me, I know this seems a little bit confusing, but it'll make a lot more sense in a few seconds. So I say 1, 2, 3, 4, 1, 2, 3, 4. And if we go back to our original diene, we can see 1, 2, 3, 4. So let's look at product 1. We can see that the hydrogen was added to the 1 carbon and the chlorine was added to the 2 carbon. This is called the 1,2 addition product because we added to carbon 1 and we added to carbon 2. Product 2 is going to be the 1,4 addition product because we added to carbon 1 and to carbon 4. I remember when I first heard these names, I was really confused. But if you break it down and number your actual diene or number starting at the carbon with the hydrogen, you can see which one is your 1,2 product and which one is your 1,4 product a lot easier. And so when do we form each one of these products? Well, as a general rule, the 1,2 product is going to be our kinetic product. And the 1,4 product is going to be our thermodynamic product. If you don't remember, kinetic means it's formed fast. It has a low activation energy relatively, and it's going to form faster at lower temperatures. And the thermodynamic product is going to be overall more stable, but it's going to have a higher activation energy, and so it's going to occur at higher temperatures. And so the reason why the 1,2 product is the kinetic product is because usually you're not going to have to go through this whole process of becoming the other resonance structure. But overall, the 1,4 addition product is going to be more stable because it's going to be less sterically hindered, like over here with this chlorine. Okay? Okay, and let's do a quick example with this. I'm going to clear my drawings. So let's say that we had, so I'm going to make an example that is not obviously a diene, but with some resonance structure stuff, we can make it into a diene. So let's say that we had OH right here, and it's attached to, actually not that. Let's do an ether. So it looks like this, and we have a double bond right here. Now, at first glance, it's not completely obvious that this could be sort of considered, if not a diene, because the word diene wouldn't go with this very well, but you can see how it can be similar to a diene when we look at its less formed resonance structure, which would occur if the double or one of the lone pairs on the oxygen creates a, hold on. Put my foot in my mouth there. What I meant when I said diene, I'm meaning it's more obviously an allylic product, an allylic carbocation, if we sort of see the actual carbocation in process. So I'm just going to do this in practice really quickly because it's easier to draw than to explain, obviously. So let's call this carbon A, and we'll call this one carbon B. So if we added our hydrogen to carbon A, so A, we would end up with this guy right here, a plus charge here, a hydrogen right here. If we added to carbon B, then we would end up with a hydrogen right here and a plus charge on carbon A. So now it should be a little bit easier to see which one of these are quote unquote allylic, or sort of cousins to our normal allylic carbocation. So if we look at product A, we can see that, oh, we have a free pair of electrons on this oxygen. It can create a double bond there and thus create this sort of resonance structure with it, with the positive charge being moved to the oxygen. Here, that positive charge is too far away from the oxygen, so we cannot do that resonance structure. As a result, using carbon A to add the hydrogen onto will create the more stable carbocation and thus be the path that we prefer when we do this addition reaction. So then I'm going to use chlorine again as our halogen, but then we would end up with our final product looking like this. Oh, let's use Br instead because I started writing it. Okay, and so our hydrogen is there, our Br is there, and thus we can sort of consider this as a type of 1,2 product. But again, in this case, it's a little bit special, but it still forms that allylic carbocation. So we have to be sure to look out for that type of intermediate, even when it's not a simple diene. Because things like this with oxygen or even nitrogen can form that allylic carbocation, allylic radical, allylic whatever. You just have to be sure to be able to look for that. Because I know that this type of question will probably trip a lot of people up, especially on ACS or even the MCAT. Okay? So I think that'll be it for this video on dienes and allylic radical or allylic carbocations that have to do with addition reactions. Next, I kind of want to go into the ideas of the molecular orbitals and how that's going to affect certain reactions with dienes. But I think this is a good stopping point for right now, and I'll see you guys next time.